the first article is this one. It talks about Dagi. Dagi is a library for creating algebraic data structures, which are basically types, if we can say, in a very simplified way. And yeah, it explains a bit how we can create these types. And this is it resembles quite a lot how you will work in a functional language like Elm or Haskell or PureScript, where your data is detached from the operations. Although here, because Fantasyland uses classes under the hood, they are kind of together, but there is no state in here. It's all pure operation. So this library lets you create some types, and well, here we'll see the first difference between going the Fantasyland way and the approaches from the that the author of the articles is using, from what we are going to write in TypeScript, right? So it's the library for creating some types for functional programs, and you can create a tag type, which is like a single constructor type, and a tag sum, which is a multiple constructor sum. So let's first create an example. This is how it looks with the library. So you can create, for example, a coordinate, and this coordinate takes 3 arguments, x, y, and z. And then you can add to the prototype of it, you can add different operations. So we are going to do something a bit different. Let me just copy this and go to the editor. So I have the repo here and the src ADTs file. Let's take that just as an example. So we'll have a type coord, right? The coordinate, and it will have 3 fields. So the x, y, and z. X is a number, y is also a number, z is also a number. Anyway, again, for the people that just joined, welcome, and please do ask questions. Otherwise, if I talk alone, it's quite boring. But if you ask questions or like want me to reiterate on something, that makes it easier. So this is just the type, but actually we see here that coord lets us do something else besides defining the type only. So we can, and I think TypeScript should allow us. Hey Chris, what's the difference on using an interface instead of a type? That's a good question. TypeScript does structural type checking. So in a sense, coord implemented like this and like that are going to be like, let's say iCoord, right? Are going to be the same. So if I define one and then I have a function that takes either of the two, I will be able to pass them to the same function. But then there are a few differences, and I think they are very well documented in the TypeScript code docs, with like the small little details of things you can do with interfaces that you cannot do with types, and the other way around. But one of those is that you can just override them. So I can add an A here. Then, hey, thank you, Fully42 for the follow. Thank you. Welcome to the fellowship of the monad. So you see, you can do this, and if I remember correctly, we say this is I chord. What error do we get here? So you see the extends. We are missing all of the fields, X, Y, Z, and A that we added here. So this is kind of like they are kind of like mutable in a sense, where I don't think we can do this with the type. Yeah, so we couldn't do this with the type. It's not common that you are going to be mutating the interface, like adding more fields, but it's possible. And I think there is something about the variadic fields that you can do with types that you cannot do with coordinates. Sorry, not with coordinates, with interface. Some people like to use types because interfaces resemble. Hello Sherman, welcome, welcome. Some people like to use types because interfaces comes more from the object-oriented world, where you would like implement the interface with the class, but you don't have to, right? It's not necessarily for that. Okay, so I think we can define chord like that, and we'll say that this will create a coordinates, right? So we'll take an X, which is a number, then we'll take a Y, also a number, and a Z, also a number, and this should return the coordinate. Before TypeScript 2.2, you could only extend from an interface, not the type, but nowadays that's not the case, I think. Interface chord 2. Yeah, you can do that. So if we return the chord, we need to add the fields, right? X, Y, and Z. So that's that's kind of the same thing that the library was doing here. And then we can define a way to translate the coordinates, right? Actually, we need to define lines first. And we can do this because TypeScript allows us to use the same identifier for a type and a value. Right? Fine. Hey, please. Thank you for the follow. Welcome to the Fellowship of the Monad. So the line, I'm gonna copy because it's going to be quite the same. It has from and to, right? So line from to, and it only takes two values to construct it. Yeah. So now we want to implement the function to translate, and you see here is where we are kind of like quite different from how Dagi does it. The Dagi library does it. So we are not going to use the prototype here, and then you see that you can do dot chaining with the method, right? We are going to instead just define this as a static. So translates takes a coordinate, which actually it's not that it takes a coordinate, it's a method of coordinates, but in practice we can say that it takes a coordinate, and then it will take chord, right? and then it will take X, Y, and Z that you want to translate to. So this will be X plus chord X, Y plus chord Y, and Z plus chord TypeScript. Pretty, do your thing. So there we go. And then we can create the line. A line is created with the origin, which is a number, and so from and to, these two are coordinates, not numbers, sorry. So this was coordinate, what I needed to add here, numbers. And then here it's when we will do things differently. We are going to import ESI, sorry, function. I must have something wrong in the configuration. What am I missing? The library is installed here. If you see that I'm missing something, post root. Module. Put here. There we go. It was probably an issue with the module type, not the src, but that should be fine. We'll check some tsconfig in my own project to see if I can figure it out. Thank you. I think I'm quite sure that it was this. I had yes next. Yeah, common yes is what should be there. Thank you. All right, so here in Dagi it uses the prototype, and then you can do the translate. Whereas here we'll define our origin. Origin with chord should take 0, 0, and 0. It looks like some alien eyes, right? And then line will pipe. Sorry. Actually, we don't need to pipe now. For line, we can say the origin, and then we can translate the origin by all these numbers. So yeah, it looks something like that. Selected one argument but got 2. Yes, indeed, because I'm taking one argument at a time. So there we go. So that's our line, and if we do, should probably see the line. Hope this doesn't give us any error. Yes, so we get from 0, 0, 0 to 1, 2, 3, and we see that we were able to translate the other line. So we could use pipe, and by suggesting to use pipe, I'm realizing that we probably want to put this in a different order, right? Where we take the coordinate at the end instead, and then we are able to pipe this. Let's split things into something that we can understand a bit better. So this is the first argument, this is the origin coordinate, and then for the second one we can pipe, and pipe is like function composition where we take one, the first argument is a value, and then we pass it to the next function in the pipeline, and that will pass it to the next one, and so on. So we will take the origin, and then we'll take our translate function that is ready to translate so it's ready to translate the origin. It takes first the three numbers that we are going to translate to, x, y, and z, and then takes a coordinate. So first it took this, and it's just now it's just a function. If we put it in the variable, like if you see, it's just a function that takes a coordinate and returns a coordinate. So we can have it here or inline, that's the same. Here using pipe doesn't bring that much of a benefit from just doing the translate, right? Function programming is like puzzle making, so satisfying. Yes, you're right. You put all of these like little pieces together, and they compose nicely, and you go home happy after work. All right. So okay, that got formatted, and we can say test, and we pass it here just so we have less mixed code. And for the sake of using pipe, I'm gonna use pipe here. Right. Okay. So that is for types that have only one element in it, right? I mean, the chord has only one constructor. It needs to take three values, but has only one constructor. There is only, we create one coordinate. Sorry. So we create one coordinate, and we need the three values to be there, or the line as well. But what about sum types? So here is the other utility from the Taggy library, tag sums. And so what are sum types? Are types that have different potential values in them. And we could use, for example, Boolean as an example. It has either true or false. It cannot be both at the same time, right? So we could define type bool, for example, and it would be one of the two. So we need a way to represent that. We can use union types in TypeScript, and we could say that it's either true or false, right? Of course, we can also say that it's true or false. and maybe this is more accurate because this is kind of like the actual representation of Boolean, right? So now we don't have the bool and it's false. So now in this case we don't have functions because true and false they don't take any arguments. Like, should the construction be functions? Yeah, so that's what I was thinking about. I don't think they need to be functions because they don't take any arguments. So coordinate is the constructor, chord here is the constructor of the type chord, and type chord needs 3 numbers to be constructed, whereas the 2 members of our bool type, true and false, they don't need any argument to be constructed. So I don't think you need them to be functions, right? I don't know how tagging works. If you pass 0 arguments here, if you still construct them as with functions or not, I don't remember properly, but yeah. Okay, and what about types that do require? I think I can export this, so then TypeScript stop giving me the errors. Some types, right? So now we have an example of a shape, and here we start to see that we use the previous examples. So a shape takes 2 coordinates in case of if it's a square, and if it's a circle takes the center, which is the coordinate, and a number, which is the radius. So let's implement the shape, type shape, right? So we know that it's a union, and that in the 2 cases, the square and the circle, which are the 2 members of the shape, both have arguments. So we need to do something like this, right? So we know there are 2 members, so we'll use a union, and for one member we'll say top left, was it? Top left and bottom right. I'm gonna copy because I'm gonna get this one wrong otherwise. This is a coordinate and bottom right is also a coordinate. And then the circle is center and radius. Oh my, which is a number. Now we need one more thing here, which is a way to differentiate if we are on which case we are. So we're going to give them a tag, which should be, this was the square, right? Then the other tag would be the circle. So now by the tag, and this is called discriminated unions in TypeScript, we can differentiate if we are on which member we are. So radius, this, okay. And we need to then implement the constructors. So square will take 2 arguments, right? And we'll return a shape. So the shape that we want to return is square. So TypeScript knows here that it can be one of the two only. So top left and bottom right. So top left is a coordinate and bottom right is also a coordinate. And similarly for the circle, we take two arguments. So first we take the radius, the center, sorry, coordinate, radius, which is the number, to return a shape. One cool thing about working with types is that here in the way we define the arguments, there is no way we return a square, right? If I say a square, okay, I need to provide top left. Top left can be the center, right? I mean, yeah, we can cheat and we can say that the bottom right is also in the center. But if we want to use the two of them, like this radius here, doesn't help, so yeah, that I need to change. Right. There we go. All right. So we have two constructors, and they have values, and they have different values. But we know that we have two of them. So if we want to implement translate, we need to handle those two cases. Right, so if we want to implement translate, or we need to give this a name. The translate line for now. These things would be like in different modules, right? So translate shape. It takes XYZ as well, but it will take the shape first. You know about, yes, I was going to mention about that one. So the thing that the library gives you, if you see this thing here, this kata, is a way to pattern match on the two types. So you give it two functions, one for each member. If you have three members, you give it three functions and so on, and you can pattern match on them. And then if you have a square, it will call this function. If you have a center, it will call this one. There are libraries to do this in TypeScript. I personally don't write so many of these, so I kind of implement these manually. And a good way to implement them manually is with what Chris shared, this FPTS code and playground. So you write the definition in what looks like Haskell types, and then it will give you the implementation of the fold function, which is the one that will pattern match. So if we define the shape, which doesn't take any type arguments, then its shape takes a square with chord, and or a circle which takes chord and number. So we can ignore the things in the bottom, but we get basically what we were implementing already. So we get the type with the two values. You can then rename them. We get the two constructors, and we get a way to pattern match on them. Yeah. So then in this function, it's basically very similar to what Dagi did in a dynamic way here. Ah, nice. So if you use, that's what Chris shared in the chat, is quite cool. So if you use record instead, you get the names, which is the cool. Let's format this a bit nicely. Right, so you give them records, and then that uses those as names. So what we get is top left, top right, center, radius, and it's quite similar to what we did. And then here we have the function that can handle the two cases. So this we wrote already. We could do it this way. I'm gonna write this by hand a bit later, and it doesn't convert into number. No, it does not. But yeah, it saves you quite some time. The interesting thing is that this is how you would do it in Haskell or in Elm or PureScript, and then the language itself has pattern matching implemented, so you don't need to implement the pattern matching function, and you don't need to implement the constructors because this thing is already the constructor. So basically all of these in TypeScript is this in Haskell. Not trying to sell Haskell, or maybe I am. Alright, so we're trying to implement the translate shape, which takes a shape first. Let's first takes the numbers, and this is so it works nicely with pipe, right? Only because of that. So then takes the shape, which can be one of the two, and it's supposed to return a shape. So what are we going to do here? Well, we are going to use the tag that we define there. So if the tag shape, the tag is equal to circle, then we return this translated circle. Else we return the translated square. So how does this work? It just creates, it translates both points, and in the case of the circle, it translates the center. All right. So we need to return square again. We are going to translate 9, which was not translate 9, was translate 4. So we give x, y, z, and then we give it the shape. We are in the circle, so let's make it the square case. Top left, then the bottom right. So top left, bottom right. There is something I'm not doing properly. There we go. So we can actually remember this because we are going to translate by the same thing. Say T, right, and then we do T as the way to translate these two. So we translated the top left and the bottom right, and we pass them. We create a new one, which is translated. Similar for the circle. We'll translate the shape center, and the shape radius we don't need to translate. So we are able to translate shapes now, and this idea of like pattern matching and checking if our shape is a square and doing something, or then checking if it's a circle and doing something will come quite a lot. That's why the library provides it directly. So what we can do instead is implement the generic version, which was what, oh no, I closed it, but which is what we had implemented by. Oh, what's wrong here? Okay. Yeah. So we can implement that, and we could call it match shape. So we're going to take first matchers. I like to call them matchers. And we need to handle the both cases. So we need a function that handles the square, and it's a function that takes top left, which is the coordinate, and bottom right, which is the coordinate. So these are the two coordinates that our square has, and needs to return some r. Any r will do. And then for the circle, we get the center and the radius, which is a number. Right. So now with this object that will pass, we can handle both cases in the same way that here kata takes the object that handles both cases, right? And then after that, well, we need to pass the shape, and we need to return r, which is the return type. So if the shape tag is a square, then we return matcher.square, and we can pass our shape top left and shape bottom right. So why do we need to do this check here? Because if I do shape dot, the only thing I have access in both branches is the tag. So for TypeScript to know, okay, the other fields are present, we need to check that the tag is square or the circle. So then there are no other cases, so TypeScript here knows that the type of the shape is the circle. So we return matchers circle, center, and shape. Now everything type checks, and we can implement our translate shapes in terms of match shape. So we can return match shape with our shape as an argument. So what are we going to do? We are going to, in case of a square, we'll do this. So it's a function that takes top left and bottom right. I need to add, this should be enough to infer. And for the circle, we take the center. We return this translated thing. So now we don't access the shape directly, but we pattern match on it. Yeah, the types checks. All right. And then whenever we work with shapes, we are going to be using this match shape, or we could call it match. In FPTS, first we're adding match shape because we could have more matchers, you know, in the same file. So in FPTS, they used to be called fault, and they're still called fault in the last version of the library, but I think it's going to change to match, if I'm not mistaken, because fault is used for something else as well. But the concept is the same. You're pattern matching on the branches because you don't know which one of them can be. So then we should have, yes, some examples here. Let's see how we can avoid typing so much. So we create a square, and then we can translate shape 3, 3. And then this one is going to be similar. We translate by 1, 2, and 3. This is a circle, so it takes first a coordinate, but the second one is just the radius. So I don't know, radius 5. So if we run that, we should get square, which is translated. We added 3 to all of them, and the bottom right is also translated, and the circle as well. So there we have the how we work with these data types with multiple constructors and multiple members, right? In Dagi, this matching is called kata, comes from katamorphism. Not what I want to do. Katamorphism, which is something in category theory. You can look up the explanation later. You don't need to know to use it. So we could define for booleans as well. We could define things like if else, for example, in terms of kind of like a ternary operation. But then here comes an interesting one, and let's see how we implement it in terms of in TypeScript. So this is about lists, and it's an interesting one. So the list has two constructors. It's a linked list. So it has the head, which is a value, and a tail, which is the rest of the list. So that's one constructor that takes the two arguments, and the other is nil. So when you don't have a list anymore, So one constructor takes 2 arguments and the other constructor takes no argument. So let's implement that. So we have a type list, and this is a new one because we didn't see any of these takes generic arguments, right? But the list will have things inside. So those will be any A, right? And then we have the 2 branches. So we have the tag, response, which has a head, which is of type A, and a tail, which is a list of A's, more. Right? And this is a recursive type, that there can be more of those. Otherwise, the other option is that there will be tag nil, and that's it. Okay. So that's our definition of a list. And let's implement, since we are at it, I'm gonna just copy this, it will make things. No, we need to implement the constructors first, sorry. So we have the constructor for cons. I takes any A. So how should it work? For working with pipe, we need to invert the arguments. So it's first it will take the tail, which is a list of A, and then it will take the head, which is an A, and it will return a list of A's, which in this case is tag cons, head, and tail. That's all we have to do. We did it similarly with the square constructor, circle constructor, but in this case it takes a type argument as well, which is what we will have inside the list. And then our cons doesn't take any value, so it's not a constructor. Sorry, our nil is just we probably need to make it the list, a function, sorry, because we need to take an argument, a type argument. But it's not because we want to take values. So this is also a list of A. Tag. There we go. So in the case of the constructors or the members of Boolean, true and false, we didn't need to make functions because they were just these 2 values. But here we need to take an argument, so there is no way to make a list of A like this. That is not a function, because this A comes from nowhere, right? So to define generic types, we need to use it as type arguments of a function. All right. Any questions? Remember that you can ask and should ask questions. Otherwise, I'm just here rambling and talking. Yeah, so the first thing we define here is map. Right? So map, what does map do? In arrays, if we do... Oh, sorry. I had the cursor in the chat. So if we check the type of array.map. Sorry, that map. We go to the definition. Well, this is not so. Yeah. Nice functors. Yeah, I don't think those easy to understand because it's a method, but basically type of map is something like this, where we have a function that goes from A to B, and then we have a list of A's, or an array of A's, an array of B's. That's what we want to implement here. We'll call it map. We'll take the function first, so there it will be an f, 2 type arguments, right? So there will be an f that goes from A to B. Then there will be a list, which is the list of A's, and we return a list of B. So how do we implement it? Well, so we can use our we didn't implement the matcher on the list, so let's quickly do that. So match list, and then we say get, cons text get. But we need another argument here, which is what's inside the list. The head is an A, and the tail is a list of A, and we return R, right? For nil, we don't take any argument, and we also need to return R. And then it takes a list of A's. So if the list is cons, then nil, so list get and list tail. Matcher, call it const, that is const. So that should be able to, we should be able to match a list, right? So what do we do when we want to implement map for the list? Well, we need to match it, right? So we'll match the list, and how do we, what do we do in each case? So in case of nil, when we don't have anything, any element, we have an empty list, well, we just, the only thing we can do is return nil, right? Which can be simplified to just that nil is the function, so it can be simplified even further there. And then in case of cons, well, we do have to do something here. So cons will give us the head and the tail, and we have a function that goes from A to B. Head is of type A, then we want to return list of B. Is it FPTS convention to name the match argument on X, on cons, and on nil? Yeah, I think so. I kind of want to, I like to give it the name of the constructor. And I think FPTS doesn't even use the object. It uses just positional arguments on a function. So if we check FPTS, for example, okay, this is where it's either has a match and a fault, they're the same. Fault, where is it? There. Match and fault are the same. So it takes on left as first argument and on right as the second argument. The either has two constructors, left and right. Yeah, so it doesn't take the object. Personally, I like the object because it's harder to make mistakes because you need to give the name to these two, especially if you have two branches that have the same argument. I guess it feels a little bit more like pattern matching when you use the constructor name. Yeah, exactly. So that's kind of why I like it. All right, so in this case here, actually we need to pass the list, right? So we are matching on a list that has A's inside, and what we want to return is list of B. Sorry, list of B. So in case of nil, well, we just return nil. There is nothing we can do. But in case of cons where we have a head and a tail, what we can do is, and the head is of type A and the tail is list of A. So we can return another cons where the head was the second argument. We'll apply the function, so it gives us we'll apply the function. So this function takes an A, head is an A, so it returns as a B, which we need to return the list of B. And for the tail, what we can do is, well, we can map it, right? We can map the tail with the function, the same function, we map the tail, which is a list of A's. There is something that is not type checking here, but I'm not sure what it is. We have the two arguments. Map the tail, we map the head. Type list. Or you can use identity instead of the nil match. Yes, you could use identity as well. No, because so you might want to do something when the list is empty, right? And I'm not passing the nil, the list here in this case. So, but tag string. I see what's the problem. Okay, that was one problem, that nil was not returning a list. Yeah, maybe. The B is what we want to return. Cons takes. But if I remove this here. So head is A and tail is of A, and we want to return of. Okay. For some reason, giving A and list of B there didn't work. Okay, what did I do differently in that process? Maybe I screw up the arguments or something. But yeah, so this is how we map the list. We in case of nil, well, there is nothing we can do. Probably you can do the short version now. In case of cons where we do have a head and a tail, we can map the tail because the tail is a list and the head is just one element, so we can apply the function. So if we construct the list, which I'm going to change the order here because it's a bit more intuitive. We do it like we take the to do the cons, we take the head first. Right, so what are your thoughts on these types of recursive solutions in JS since there is no take-call optimization? Yeah, it can be quite yeah, it's not really performant. You probably don't want to use these for like long lists, right? But for cases when you don't have a recursive type that can go forever, and then it's fine. It should be fine at least. I think there are some techniques to work around it if you do need recursive types, but yeah, I don't think this is a case where you want to have 1,000 elements in this list, right? Because then mapping will be much slower than that of an array. But we can construct, so I don't know, numbers. So we can say cons of a list that has 1, then the second is a tail, so that's can be another cons which has a 2, and the second of that is also a tail, so we can say cons 3, right? And we close. This one needs one more argument, and we can say nil. And now we have a list of numbers, right? Which has 1, 2, 3. So if we map it, we say that we map, I don't know, we can map it to like string, right? So we say n, and we're going to use pipe here, so we have our numbers. Then we map our end to string. It should log the list with strings, with numbers converted to strings. So yeah, as you see here, we have a cons. The first cons has number 1 converted to string. The second cons in the head has the 2. The third cons has the 3, and then the tail is just an object, which is the nil, right? Can do JSON stringify. So we log the whole thing. Yeah, so cons 1, 2, and 3. Oh, nice. Here, nice. Didn't know about that one. And there are some other functions that we implement. We can implement from, it's probably from array, right? So this is an interesting one. And then we don't need to create it manually like this. So from array. So how will that one work? We take an array. So the array is of any ace, right? So that's array of A, and we return a list of A. So how do we do it? We can reduce, and I think it's using reduce right. Yes, it's using reduce right because we want to construct it in the same way as you saw here, like from the right to the left. And we'll start with nil, and we'll have the list that we are accumulating. So this will be like the tail and then the head, and we return const head and tail, which is, there we go. So if we do from array, and we do 1, 2, 3, we should get the same result. As we got before. Yep, so we get 1, 2, 3, and then the nil. So it was here, then the right, I don't know, 5. Have format on save and it jumps, I don't know why. There we go. Okay, so the tail at the end is a tag, it's nil. Thank you, Chris, for that one. So it's the same thing as this one, but we don't need to manually do all of these cons. You can say though that this is equivalent to, actually it's the same. Okay, so toArray is an interest, and that, I think that would be the last one. There are exercises to implement, like filter, reduce, but we'll skip it for the sake of time. Hey Bob Rost, how you doing? Welcome to the stream. We are doing TypeScript and functional programming today. So it was toArray. Again, we take our A as an argument, and then we have A's as well, but then this is the list of A's, and we want to return an array of A's instead. So we are going to match in the list. We'll take A's and we'll return an array of A's. I just spent an hour setting up my dad's Xbox and getting my brother to use a password manager. Nice. I mean, maybe you didn't want to do it, I don't know. But it's good to convert people to use password manager. So what will we do? In the case of nil, what will return in the case of nil? So nil is the empty list, so we need to return the empty array, right? And that is basically an array of A's. Not that fun, okay. It wasn't fun then. Const, on the other hand, will take the head and the tail. So, and we need to return an array of A's. So what we can do is, we have the head, which is type A, and we can spread the toArray of the tail. So we spread the rest and we get errors. Type list AI is missing the following properties. Sorry, I forgot to post this here. There we go. So I could have been at my beautiful PC playing with VS Code, but you know how it is when family thinks that the programmer is tech support. Yeah, well, but it's also family, right? So, but yes, I know you have to fix the printer and whatnot. So in this case, if we do from array and to array, we should get the same. So console log. Not that fun, depends on what I'm doing. Yes, of course. So if we do to array and from array, we should get the same array back. Yeah, there are a lot of things one would rather do. You're right. Okay, so yeah, we get back the array, right? To and from, and it gives us the same thing, and we can give it a few more. I have no idea what that PS is. It's a programming language that compiles to JavaScript. So it's TypeScript. Okay, so that's all for the article on tagging, and we are going to use this approach on the next articles, right? When we start like implementing different algebraic data types, ADTs, we're going to start using these approaches, and we'll define all the types